In the next set of lessons, we will discuss in more detail some of the key resource management components in operating systems. First, we will look at how the operating system manages CPUs and how it decides how processes and their threads will get to execute on those CPUs. And this is done by the scheduler. We will review some of the basic scheduling mechanisms, some of the scheduling algorithms and data structures that they use. And we will look in more detail at some of the scheduling algorithms used in the Linux operating system, the Completely Fair Scheduler and the Of1 Scheduler. We will also look at certain aspects of scheduling that are common for multi-CPU platforms. This includes multi-core platforms and also platforms with hardware-level multi-threading. For this, we will use the paper Chip Multi-Threaded Processors Need a New Operating System Scheduler in order to demonstrate some of the more advanced features that modern schedulers should incorporate. In this lesson, we will be talking at length about scheduling and OS schedulers. So continuing with our visual metaphor, we'll try to visualize what are some of the issues when it comes to OS scheduling. Using our toy shop analogies, we'll think of an OS scheduler and we'll compare it with a toy shop manager. Like an OS scheduler, the toy shop manager schedules work in the toy shop. For a toy shop manager, there are multiple ways how it can choose to schedule the toy shop orders and dispatch them to workers in the toy shop. First, the toy shop manager can dispatch orders immediately as soon as they arrive in the toy shop. Or the manager may decide to dispatch the simple orders first. Or even conversely, the manager can decide to dispatch the complex orders as soon as they arrive in the shop. The motivation for each of these choices is based on some of the high-level goals of the manager and how he wants to manage the shop and utilize the resources in the shop. Let's investigate these choices a little more. If the manager wants low scheduling overhead, not to have to analyze too much what he needs to do when an order comes, he can choose to dispatch the orders immediately. The scheduling in this case is very simple. We can think of it as a FIFO. First order that comes in is the first one that will be served. If the manager is concerned with the total number of orders that get processed over a period of time, it would be good to dispatch the simple orders as soon as they arrive. They will be the ones that will be completing more quickly, and that will maximize this particular metric. Obviously, in order to do this, the manager has to spend a little bit more time whenever an order comes because he needs to check what kind of order that is, whether it's going to be a simple one or not, and then decide what to do with it. So basically, it will be important for the manager to be able to assess the complexity of the orders. On the other hand, on each of the workbenches in the shop, there may be different kinds of tools, and these simple orders, these may not really exercise all of these tools. They may not require the use of all aspects of the workbenches. So if the manager wishes to keep all of the resources that are available on the workbenches as busy as possible, he may choose to schedule complex orders as soon as they arrive, and then whenever simple ones come in, perhaps the workers can pause the processing of the complex order to get a simple one in and to finish it as soon as possible. In comparison, the scheduling options for a toy shop manager are surprisingly similar to those of an OS scheduler. For an OS scheduler, these choices are analyzed in terms of tasks, which is either a thread or a process, and these are being scheduled onto the CPUs that are managed by the OS scheduler, like the workbenches in the case of the toy shop manager. For an OS scheduler, we can choose a simple approach to schedule tasks in a first-come, first-served manner. The benefit is that the scheduling is simple and that we don't spend a lot of overhead in the OS scheduler itself. Using a similar analogy to what the toy shop manager was thinking of when he chose to dispatch the simple orders first, an OS scheduler can dispatch simple tasks first. The outcome of this kind of scheduling can be that the throughput of the system overall is maximized. And there are schedulers that actually follow this kind of algorithm, and those are called shortest job first. So simple in terms of the task is equal to its running time, so shortest job first. And finally, the scheduling logic behind assigning complex tasks first is similar to the case in the toy shop. Here, the scheduler's goals are to maximize all aspects of the platform, so to utilize well both the CPUs as well as any other devices, memory, or other resources that are present on that platform. As we move through this lesson, we will discuss some of the options that need to be considered when designing algorithms such as these, and in general, we will discuss various aspects of the design and implementation of OS schedulers. We talked briefly about CPU scheduling in the introductory lesson on processes and process management. We said that the CPU scheduler decides how and when processes access the shared CPUs in the system. In this lesson, we'll use the term task to interchangeably mean either processes or threads, since the same kinds of mechanisms are valid in all contexts. The scheduler concerns the scheduling of both user-level processes or threads, as well as the kernel-level threads. Recall this figure that we used when we talked originally about processes and process scheduling. The responsibility of the CPU scheduler is to choose one of the tasks in the ready queue, a process or a thread. We said we'll just use the term task to refer to both, and then to schedule that particular task onto the CPU. Threads may become ready, so they may enter the ready queue after an I/O operation they have been waiting on has completed, or after they have been woken up from a wait on an interrupt, for instance. A thread will enter the ready queue when it's created, so when somebody has forked a new thread. And also a thread that maybe was interrupted while executing on the CPU because the CPU has to be shared with other threads. That thread, it was ready, it was executing on the CPU, so after it has been interrupted, it continues to be ready, so it will immediately go into the ready queue. So to schedule something, the scheduler will have to look at all of the tasks in the ready queue and decide which is the one that it will dispatch to run on the CPU. Whenever the CPU becomes idle, we have to run the scheduler. For instance, if a thread that was executing on the CPU makes an I/O request and now it has to wait in the I/O queue for that particular device, the CPU is idle. What happens at that moment? We run the OS scheduler. The goal is to pick another task to run on the CPU as soon as possible and not to keep the CPU idle for too long. Whenever a new task becomes ready, so a task that was waiting on an I/O operation or was waiting on an interrupt or some kind of signal, or whenever a brand new task was created for the first time, for all of these reasons, again, we need to run the scheduler. The goal is to check whether any of these tasks are of higher importance and therefore should interrupt the task that's currently executing on the CPU. A common way how schedulers share the CPU is to give each of the tasks in the system some amount of time on the CPU. So when a time slice expires, when a running thread has used up its time on the CPU, then that's another time when we need to run the scheduler so as to pick the next task to be scheduled on the CPU. Once the scheduler selects a thread to be scheduled, the thread is then dispatched onto the CPU. What really happens is we perform a context switch to enter the context of the newly selected thread, and then we have to enter user mode and set the program counter appropriately to point to the next instruction that needs to be executed from the newly selected thread. And then we're ready to go. The new thread starts executing on the CPU. So in summary, the objective of the OS scheduler is to choose the next task to run from the queue of ready tasks in the system. The first question that comes to mind is which task should be selected? How do we know this? The answer to that will depend on the scheduling policy or the scheduling algorithm that is executed by the OS scheduler. We will discuss several such algorithms next. Another immediate question is, how does the scheduler accomplish this? How does it perform whatever algorithm it needs to execute? The details of the implementation of the scheduler will very much depend on the run queue, on the data structure that we use to implement this ready queue. That's called the run queue. The design of the run queue and the scheduling algorithm are tightly coupled. We will see that certain scheduling algorithms, they demand a different type of run queue, a different data structure, and also that the design of the run queue, it may limit in certain ways what kinds of scheduling algorithms we can support efficiently. So the rest of the lecture will focus on reviewing different scheduling algorithms and run queue data structures. For this first discussion of scheduling algorithms, I want to focus on what we call run-to-completion scheduling. This type of scheduling assumes that as soon as a task is assigned to a CPU, it will run until it finishes or until it completes. Let me list first some of the initial assumptions we will make. We will consider that we have a group of tasks that we need to schedule. I'll refer to these also as threads and jobs and similar terms. Let me also, to start with, assume that we will know exactly how much time these threads need to execute. So there will be no preemption in the system. Once a task starts running, it will run to completion. It will not be interrupted or preempted to start executing some other task. And also, to start with, let me assume that we only have a single CPU. We will relax these requirements further as we go through this lesson. Now, since we will be talking about different scheduling algorithms, it will be important for us to be able to compare them, so we'll want to think about some useful metrics. When it comes to comparing schedulers, some of the metrics that can give meaningful answers regarding those comparisons include throughput, the average time it took for tasks to complete, the average time the tasks spent waiting before they were scheduled, overall CPU utilization. We will use some of these metrics to compare some of the algorithms that we will talk about. The first and the simplest algorithm we'll talk about is first come, first serve. In this algorithm, tasks are scheduled on the CPU in the same order in which they arrive, regarding of their execution time, of load in the system, or anything else. When a task completes, the schedule will pick the next task that arrived in that order. Clearly, a useful way to organize these tasks would be in a queue structure so that tasks can be picked up from it in a FIFO manner. Whenever a new task becomes ready, it will be placed at the end of the queue, and then whenever the scheduler needs to pick the next task to execute, it will pick from the front of the queue. To make its decision, all the scheduler will need to know will be the head of the queue structure and how to dequeue tasks from this queue. So basically, for first come, first serve scheduling, some FIFO-like queue would be a great run queue data structure. Now, let's take a look at a scenario in which these three tasks, T1, T2, and T3, have the following execution times. T1 is 1 second, T2 is 10 seconds, and T3 is also 1 second. And let's assume they arrive in this order. So T1 followed by T2 followed by T3. So this is how they'll be placed in the run queue. Now, let's look at throughput as a metric for this kind of system that uses the first come, first serve scheduler. We have three tasks. To execute them one after another, we will take a total of 12 seconds, 1 plus 10 plus 1. So the scheduler, on average, achieves a quarter of a task per second, so 0.25 tasks per second. If you're interested in the average completion time of these tasks, the first task will complete in 1 second, since it will start immediately. The second task, it will complete at time t11. It will have to wait 1 second for the first task to complete, and then it will execute for 10 seconds. And then the third task, it will complete at time t12 because it will have to wait for the 11 tasks for T1 and T2 to execute until it starts and executes for 1 second. So if we compute the average completion time in this system, we see that it is 8 seconds. If we're interested in the average wait time for the three tasks in the system, then the first task started immediately. The second task started a second later because it had to wait for T1 to complete. And then the third task had to wait for 11 seconds before it started executing. So the average wait time for these three tasks is 4 seconds. So we have a simple scheduling algorithm. However, probably we can do a little bit better in terms of the various metrics that we are able to achieve with this algorithm when we try something else. So we see that first come, first serve is simple, but the wait time for the tasks is poor, even if there is just one long task in the system that has arrived ahead of some shorter tasks. So to deal with this, we can look at another algorithm that's called shortest job first. And the goal of this algorithm is to schedule the tasks in the order of their execution time. Given the previous example with tasks T1, T2, and T3, the order in which we want to execute them would be T1 followed by T3 and then T2, the longest task at the end. And for tasks that take the same amount of time to execute, perhaps we break ties arbitrarily. Now, if we organize our run queue the same way as before, adding new tasks to the run queue will be easy, since it will just mean that we have to add a task at the tail of the queue. However, when we need to schedule a new task, we'll need to traverse the entire queue until we find the one with the shortest execution time. So a run queue really won't be a FIFO run queue anymore, since we will need to remove tasks from the queue in a very specific order based on execution time. One thing we can do is we can maintain the run queue as an ordered queue so that tasks, when they're inserted into the queue, are placed in the queue in a specific order. It will make the insertion of tasks into the queue a little bit more complex, but it will keep the selection of a new task as short as it was before. We just need to know the head of the queue. Or our run queue doesn't really have to be a queue. It can be some tree-like data structure in which the nodes in this tree are ordered based on their execution time. When inserting new nodes in the tree, new tasks in this tree, the tree may need to be rebalanced. However, for the scheduler, it will be easy since it will always have to select the leftmost node in the tree. If the tree is ordered, the leftmost node will have the smallest execution time. So we have a queue, a tree. This illustrates really that the run queue doesn't really have to be a queue. It can be other type of data structure, and we'll see that it often is based on whatever is appropriate for the scheduling algorithm. Let's do a quiz in which we analyze the performance metrics for shortest job first. To do this, let's assume first that shortest job first is used to schedule 3 tasks, T1, T2, and T3. Also, let's make the following assumptions. The scheduler will not preempt the task, so this will be the run-to-completion type of model that we discussed so far. We'll assume that we know the execution times of these tasks, and we'll use the same values as we used before. So T1 and T3 are 1 second, and T2 is 10 seconds. And let's assume that they all arrive at the same time. So we will start analyzing the system from some time T0 when all of these tasks are actually in the system already. For this system, calculate the throughput, the average completion time, and the average wait time using the shortest job first algorithm. Let's look at the answer to this question. So first, given that we have a shortest job first algorithm, and these are the execution times of the tasks, what is going to be the execution order of these tasks? Clearly, they'll have to execute in this order. So T1 followed by T3 or the other way around, and then followed by T2. Now that we know the order of the tasks, we can actually compute these 3 metrics. To compute the throughput, again, we have 3 tasks in the system. All of the 3 tasks get processed in 12 seconds, so 1 plus 10 plus 1. So we have a total throughput of 0.25 tasks per second. So nothing has really changed compared to the first-come, first-serve algorithm here. Now, if we look at the average completion time, the first task, T1, completes in 1 second. The second task, T3, that one completes in another 1 second, so in 2 seconds. And then the third task, T2, well, that one will need another 10 seconds, so it will complete at time T12. So the average completion time is 1 plus 2 plus 12 over 3. That's 5 seconds. That's already way better than the 8 seconds that we saw in the first-come, first-serve algorithm. If we look at the average wait time, the first task, T1, it didn't wait at all. It started executing immediately. T3, it had to wait 1 second. T2 had to only wait 2 seconds since both T1 and T3 are short. So the average wait time in this system is only 1 second. That is way better than the 4 seconds that first-come, first-serve resulted in. So if we care about metrics such as these, clearly shortest job first would be a better algorithm than first-come, first-serve. So far in our discussion, we assumed that a task that's executing on the CPU cannot be interrupted, cannot be preempted. Let's now relax that requirement and start talking about preemptive scheduling, scheduling in which the tasks don't just get the CPU and hog it until they're completed. So we'll consider preemption first in the context of the shortest job first algorithm. And for this, we will also make another assumption, or we will modify another assumption that we made earlier. Tasks don't all have to arrive at the same time. So we're going to look at a system that has 3 tasks, T1, T2, and T3. We know their execution time, so that assumption still holds. And we will assume that they arrive now at arbitrary times. So in this particular case, T2 arrives first. When T2 arrives, it's the only task in the system. T1 and T3 haven't arrived yet, so the scheduler will clearly schedule it and it will start executing. When the tasks T1 and T3 show up, then T2 should be preempted. We're using shortest job first, and T1 and T3 have shortest jobs compared to T2. The execution of the rest of the scenario will look something as follows. Let's say at T2, when the tasks T1 and T3 show up, T1 is the one that's scheduled next. Then once it completes, T3 is the next one that has the shortest running time. So T3 will execute. And once these two have completed, then T2 can take the remaining of its time to execute. So basically what would need to happen in order for us to achieve this kind of behavior is that whenever tasks enter the run queue, like T1 and T3, the scheduler needs to be invoked so that the scheduler can inspect their execution times and then decide whether to preempt the currently running task, task T2, and schedule one of the newly readied tasks. Now, so far we talked as if we know the execution time of a task, but its principle, that's hard to tell. It's really hard to claim that you know what is the execution time of a task. There are a number of factors that depend on the inputs of the task, on whether the data is present in the cache or not, which other tasks are running in the system. So in principle, we have to use some kind of heuristics in order to estimate, or rather guesstimate, what the execution time of a task will be. When it comes to the execution time, so the future execution time of the task, it's probably useful to consider what was the past execution time of that task or that job. So in a sense, history is a good predictor of what will happen, so we will use the past execution time to predict the future. For instance, we can think about how long a task ran the very last time it was executed, or maybe we can take an average over a period of time or over a number of past runs of that particular task. We call this scenario in which we compute averages over a period of the past a windowed average, so we compute some kind of metric based on a window of values from the past and a window of historic values, and then use that average for prediction of the behavior of the task in the future. Shortest job considers the execution time of the tasks in order to decide how to schedule tasks and when to preempt a particular task. Another criteria for driving those decisions may be that the tasks have different priority. Tasks that have different priority levels, that's a pretty common situation. For instance, we have certain operating system level threads that run OS tasks that have higher priority than other threads that support maybe user-level processes, or even within a user-level process, maybe certain threads that are intended to run when there is user input. Such threads may have higher priority compared to other threads that just do some background processing or long-running simulations. In such scenarios, the scheduler will have to be able to run the highest priority task next. So clearly, it will have to support preemption. It will need to be able to stop a low priority task and preempt it so that the high priority one can run next. So let's look at now the same example from before, except now we're going to use priority scheduling, and we need to know the task's priorities. And in this particular example, the priorities P1, P2, and P3 are such that the first thread, T1, has the lowest priority, followed by the second thread, so it's priority P2, and then finally the third thread, T3, has the highest priority P3. Again, we start with the execution of T2 since it's the only thread in the system. Now, however, when T1 and T3 become ready at this particular point of time, when time is 2, we'll have a very different execution compared to the shortest job first with preemption scheduler. So when we look at the priorities, we see that T3 has the highest priority, P3. So when threads 1 and 3 become ready and they arrive at this particular moment, thread 2 is first going to be preempted and the execution of thread 3 will start. So thread 3 has the highest priority. When thread 3 completes, at that point thread 2 has the lower priority. So we'll have to give the CPU to thread 2. And now it's pretty unfortunate that poor thread 1 will have to wait for all this time before it can execute, but a priority-based scheduling is only going to look at the priorities of the thread. So thread 1 is not going to really start running until the 11th second in this time graph, and then it will complete at time T12, as the entire schedule will complete at that time as well. In this example, we were looking up this table, but in principle, our scheduler, let's take a quiz now in which we will compute some of the performance metrics for a preemptive scheduler. An OS scheduler uses a priority-based algorithm with preemption to schedule tasks. Given the values that are shown in this table, complete the finishing times for each of the 3 tasks. Also assume that the priorities are such that P3 is lower than P2 and then it's lower than P1. Write the finish times of each of the tasks in the boxed areas provided here. To answer this question, let's look at the execution scenario in this system. T3 is the first one to arrive in the system, and it will be the only task for a while, so T3 will be the first one to be scheduled. At time T3, it will be preempted, and task T2 will start executing because it has higher priority than T3. At time T5, task 1 will arrive, and that one will execute for 3 seconds. T1 will preempt the execution of T2 because T1 has higher priority than T2, according to this assumption. And then we have 2 more seconds to finish the execution of T2, followed by the execution of the lowest priority task, T3. So that one, we had 1 more second remaining. So the finishing times of the 3 tasks, according to this diagram, are going to be 8 seconds, 10 seconds, and 11 seconds, respectively. An interesting phenomenon called priority inversion happens once we introduce priorities into the scheduling. Consider the following situation, and we'll use the shortest job first scheduling to illustrate what happens. We have 3 threads. The first one has the highest priority, and P3 is the lowest priority. So T1 is the highest priority thread, and T3 is the lowest one. For this example, we've left out the execution times. Just assume that they take some longer amount of time, all these tasks, and that the time graph continues into the future. Initially, T3 is the only task in the system, so T3 executes, and let's say that T3 also acquired a lock. Now, T2 arrives. T2 has higher priority than T3, so T3 will be preempted, and T2 gets to execute. Now, time 5, T1 arrives. It has higher priority than T2, so T2 will be preempted. And then T1 executes for 2 time units, and at that point, it needs to acquire a lock, and this happens to be the exact same lock that's already held by T3. Unfortunately, that won't happen. T1 cannot acquire the lock, so T1 at that point is put on a wait queue associated with the lock. We schedule the next highest priority task that's runnable. That's going to be T2, and then T2 will execute as long as it needs. And let's say in this case, we locked out. T2 really only needed to execute for 2 more units. At that point, T2 completes. We schedule the next highest priority runnable task. The only runnable task in the system is T3, so T3 will get to execute. And in fact, T3 will execute for as long as it needs to until it releases the lock. Only after T3 releases the lock will T1 become runnable, and then once T1 becomes runnable again, it is the highest priority thread, so T1 will preempt T3, and T1 will continue its execution. So it will acquire the lock and continue executing. So based on the priority in the system, we were expecting that T1 will complete before T2, and then T3, the lowest priority thread, will be the last one to complete. However, that's not what happened, and the actual order of execution was as follows. T2, the medium priority thread, followed by T3, the lowest priority thread, followed by, finally, T1, the highest priority task in the system. So the priorities of these tasks were inverted. This is what we call priority inversion. A solution to this problem would have been to temporarily boost the priority of the mutex owner. What that means is that at this particular point, when the highest priority thread needs to acquire a lock that's owned by a low priority thread, the priority of T3 is temporarily boosted to be basically at the same level as T1. Then T1 could not have proceeded just as before, given that the lock is owned by somebody else. However, instead of scheduling T2, we would have scheduled T3. Its priority would have been temporarily boosted to that of T1, so it would have been higher than T2. And then T2 would have completed, and so at least we would have been able to go ahead and start executing T1 at this particular point, and then we would not have had to wait for T2 to complete, for the medium priority thread to get in the middle. This technique of boosting the priority of the mutex owner, this is why, for instance, it is useful to keep track of who is the current owner of the mutex. This is why we said we want to have this kind of information in the mutex data structure. And obviously, if we're temporarily boosting the priority of the mutex owner, we should lower its priority once it releases the mutex. The only reason why we were boosting its priority was so as to be able to schedule the highest priority thread to run as soon as possible. So we wanted to make sure that the mutex is released as soon as possible. This is a common technique that's currently present in many operating systems. Now, when it comes to running tasks that have the same priority, we have other options in addition to the first come, first serve or shortest job first that we discussed so far. A popular option is so-called a round-robin scheduling. So let's say we have the following scenario. We have 3 tasks. They all show up at the same time, and they're all in the queue. With round-robin scheduling, we'll pick up the first task from the queue, just like with the first come, first serve scheduling. Now, let's say we pick up T1. That's the first in the queue, so T1 starts executing. Now, after executing for 1 time unit, the task stopped because it now needs to wait on an I operation, so it will yield the CPU and be blocked on that I operation. This is unlike what we saw in first come, first serve, where we were assuming that each of the tasks executes until it completes. If that's the case, we'll schedule T2, T3 will move to the front of the queue. Now, potentially, T1 will complete its I operation. It will be placed at the end of the queue behind T3. Then when T2 completes, we will schedule T3. The execution time here, we assume, is only 2 time units. And then when that one completes, we'll finally pick up T1 from the queue and complete T1. If T1 had not been waiting on I/O, then the execution based on T1, T2, T3, the order in which they were placed in the queue, would have looked something like this. So each of the tasks executes one by one in a round-robin manner, and the queue is traversed in a round-robin manner one by one. We can further generalize round-robin to include priorities as well. Let's assume that the tasks don't arrive at the same time, T2 and T3 arrive a little later, and that their priorities are as follows. T1's priority is the lowest, and T3's is the highest. So in that case, what happens is that when a higher priority task arrives, the lower priority task will be preempted. If T2 and T3, however, have the same priorities, then the scheduler will just go round-robin between them until they complete. So basically, in order to incorporate priorities, we have to include preemption, but otherwise, the tasks will be scheduled from the queue like in first come, first serve, so the first task from the queue. However, we will release the requirement that they have to control the CPU, that they have to execute on the CPU until they complete. Instead, they may explicitly yield. And we will just round-robin among the tasks on the queue. A further modification that makes sense for round-robin is not to wait for the tasks to yield explicitly, but instead to interrupt them so as to mix in all of the tasks that are in the system at the same time. We call such mechanism time slicing. So let's say we can give each of the tasks a time slice of 1 time unit, and then after a time unit, we will interrupt them, we will preempt them, and we will schedule the next task in the queue in a round-robin manner. So we will cycle through them T1, T2, T3, and then again. We will focus our discussion next on time slicing to better explain this mechanism. We mentioned time slices very briefly in the introductory lesson on processes. To define it more specifically, a time slice is the maximum amount of uninterrupted time that can be given to a task. It is also referred to as a time quantum. The time slice determines the maximum amount. That means that a task can actually run a less amount of time than what the time slice specifies. For instance, the task may need to wait on an I operation or to synchronize with some other tasks in the system on a mutex that's locked. In that case, the task will be placed in a queue, will no longer be running on the CPU. The task will run less amount of time. Once it's placed on the queue, the scheduler will pick the next task to execute. Also, if we have a priority-based scheduling, a higher priority task will preempt a lower priority one, which means that the lower priority task will run less amount of time than the time slice. Regardless of what exactly happens, the use of time slices allows us to achieve for the tasks to be interleaved. They will be time-sharing the CPU. For I/O-bound tasks, this is not so critical since they're constantly releasing the CPU to wait on some I/O event. But for CPU-bound tasks, time slices is the only event how we can achieve time sharing. They will be preempted after some amount of time as specified by the time slice, and we will schedule the next CPU-bound task. Let's look at some examples now. Consider, for instance, the simple first-come, first-serve and shortest job first schedulers that we saw earlier in this lesson. They both had a same mix of tasks with same arrival times, but led to different metrics. And note that the metrics that we computed for first-come, first-serve also apply to a round-robin scheduler that doesn't use time slices. given that these tasks don't perform any I/O, they just execute for some fixed specified amount of time, then Roundrobin would have scheduled them one and after another the way they showed up in the queue, and that would have been identical to first come, first serve. Now let's calculate the metrics for a Roundrobin scheduler with time slices, and let's say we'll first look at a time slice of 1. The execution of these tasks will look as follows. T1 will execute for 1 second. That happens to be exactly the time that T1 requires, so T1 will complete. Then with time slicing, we would have preempted the execution of T1 anyways. We will execute T2. Now T2 needs more time to execute, 10 seconds, so it will actually be preempted. T3 will run for a second. At the time when we're about to preempt it, T3 will anyways complete, and the only runnable task in the system is T2, and we will execute T2. So T2 will run for the remainder of the time. Now, if we look at some of the metrics for throughput, we'll see we'll have the exact same thing. It still takes us 12 seconds to complete these 3 tasks. So the throughput will again be the same as in the previous 2 systems. Looking at the wait time, we have a wait time of 0, 1, and 2 for each of the tasks respectively. So our wait time is 1 second. If we look at the average completion time, the tasks complete at 1, at 12, and at 3 seconds respectively. So the average completion time is 5.33 seconds. So without even knowing what are the execution times of these tasks, with a time slice of 1, we were able to achieve a schedule that's really close to this best one that we saw before, the shortest job first one. This is good. We keep some of the simplicity that we had in first come, first serve. We don't need to worry about figuring out what is the execution time of the task. And yet we were able to achieve good wait time and good completion time for all of the tasks. So some of the benefits of this time slice-based method, particularly when the time slice is relatively short, like in this case, is that we end up with a situation where the short tasks finish sooner. So T3 was able to complete much sooner than in the first come, first serve case. And we're also able to achieve a schedule that is more responsive, and any I/O operations can be executed and initiated as soon as possible. So for instance, consider if T2 is a task that the users interact with. It will be able to start as soon as possible, only 1 second into the execution. The users will see that it is running, and yet it will be preempted to squeeze in T3 at this point. If T2 needs to initiate any I/O operations, those will be initiated during this interval that it's running at this point. That would not have been the case with the shortest job first scheduler, because T2 would have only been scheduled after all of the shorter jobs complete, so T1 and T3 in that case. The downside is that we exaggerated so far a little bit in that we had these tasks immediately starting their execution after the previous one was interrupted. However, there are some real overheads. We have to interrupt a running task, we have to run the scheduler in order to pick which task to run next, and then we actually need to perform the context switch when we're scheduling from the context of one task to another. All of these times are pure overhead. There's no useful application processing that's done during those intervals. Note that these overheads, so if we have a time slice of 1, these timeouts for the timer will appear during the execution of task T2, except at that point, since there are no other runnable tasks in the system, we're really not going to be scheduling or context switching, and that's the dominant part of the overhead. And exactly how these ticks are handled, we're not really going to discuss further in this class. The dominant sources of these overheads will impact the total execution of this timeline, and increasing the time will cause the throughput to go down. Each of the tasks will also start just a little bit later, so the wait time will actually increase a little bit. And the completion time for each of the tasks will be delayed by a little bit, so the average completion time will increase as well. The exact impact on these metrics will depend on the length of the time slice and how it relates to the actual time to perform these context switching and scheduling actions. So as long as the time slice value is significantly larger than the context switch time, we should be able to minimize these overheads. In general, we should consider both the nature of the tasks as well as the overheads in the system when determining meaningful values for the time slice. We saw in the previous Moore-cell that the use of time slices delivers certain benefits. We're able to start the execution of tasks sooner, and therefore we are able to achieve an overall schedule of the task that's more responsive. But that came with certain overheads. So the balance between these two is going to imply something about the length of the time slice. We will see that to answer this question, how long should a time slice be, the balance between these two differs if we're considering I/O-bound tasks, so tasks that mostly perform I/O operations, versus CPU-bound tasks. So these are tasks that are mostly executing on the CPU and don't do any I/O or do very little I/O. We will look at these two different scenarios next. Let's first look at an example in which we will consider two CPU-bound tasks. So these are tasks that are mostly just running on the CPU and don't perform any I/O. Let's assume their execution time is 10 seconds. And in this system, let's assume that the time to context switch from one context to another takes just 0.1 seconds. For this scenario now, let's take a look at what will happen when we consider two different time slice values, time slice of 1 second and time slice of 5 seconds. With a time slice of 1 second, the execution of these two tasks will look something as follows. And let's assume that the thicker vertical bars are trying to capture this context switch overhead in this case. For the time slice value of 5 seconds, the schedule will look as follows, and the context switch overhead is only paid at this particular point. That's in contrast with having to context switch at every single one of these vertical bars here. Now, if we compute the metrics for throughput, average wait time, and average completion time for these tasks, we will obtain the following results. To complete the throughput, we calculate the total time that it took to execute these tasks and divide it by 2, by the number of tasks. To complete the average wait time, we look at the start time of each of the tasks and divide that by 2, the number of tasks. And to complete the average completion time, we look at when each of the two tasks completed, and then we average that. And the detailed calculation for both of these are in the instructor's notes. Looking at these metrics, we see that for throughput, we're better off choosing a higher time slice value. For completion time, also we're better off choosing a higher time slice value. And then for the average wait time of the tasks, we're actually better off choosing a lower time slice value. However, these are CPU-bound tasks. We don't really care about their responsiveness, and the user is not necessarily going to perceive when they started. The user really cares about when they complete and overall when all of the tasks submitted to the system complete. So this really means that for CPU-bound tasks, we're really better off with choosing a larger time slice. This is the winning combination for us. In fact, for CPU-bound tasks, if we did no time slicing at all, so like the time slice value is infinite, we'd end up with absolutely the best performance in terms of the throughput and the average completion time, so the metrics that we care for when we run CPU-bound tasks. Yes, of course, the average wait time of the task will be worse in that case, but we don't care about that. It's CPU-bound task. We won't notice that. So in summary, a CPU-bound task prefers a larger time slice. Now, let's try to see what will happen if we're considering two I/O-bound tasks. And again, we'll think of two tasks that have execution time of 10 seconds and in a system that has a context switch overhead of 0.1 second. And let's also assume that the nature in which these I/O calls are performed is that a task issues an I/O operation every 1 second. And let's also assume that every single one of those I/O operations complete in exactly half a second. If we look at the timeline, it looks identical as what we saw in the case for the CPU-bound jobs with a time slice of 1 second. This makes sense because exactly after 1 second, the tasks are, in this case, not exactly preempted. They actually end up issuing an I/O operation, so yielding voluntarily regardless of the fact that the time slice is 1. So if we look at the performance metric for this case, they will be identical to the previous case in the case of the CPU-bound tasks. Now, if we look at the second case that has a time slice value of 5 seconds, we see that the timelines, the schedules of the two tasks, are identical to the case when we had a much smaller time slice value of 1 second. Similarly, obviously, if we compute the metrics, they will be identical. It's for two identical schedules. The reason for this is that at this particular moment, we're not exactly time slicing. We're not interrupting the tasks in either one of these cases. The I/O operation, again, is issued every 1 second, So regardless of the fact that in this scenario the time slice value is much longer, we still end up issuing an I/O operation at the end of the first second, and therefore the CPU is at this point released from T1, T1 yields, and T2 is free to be scheduled and to start executing. So one conclusion that you can make from this is that for I/O-bound tasks, the value of the time slice is not really relevant. Well, let's not draw that conclusion that fast. Let's look first at a scenario where only T2 is an I/O-bound task. T1 is a CPU-bound task, as what we saw in the previous morsel. In that case, the execution for the two tasks T1 and T2, when the time slice is 1, will look the same. The one difference is that in the event of T1, we preempted after 1 second, whereas in the case of T2, the I/O-bound task, after 1 second, it voluntarily yields since it has to go and wait for an I/O operation. In the case of 5 seconds, the execution of T1 and T2 will look something as follows. T1 will run for 5 seconds, and at that point, its time slice will expire, so it will be preempted. T2 will be scheduled, and as an I/O-bound task, T2 will yield after 1 second because of waiting on an I/O operation. At that point, T1 will be scheduled again. Now, at this point, T1 is actually complete, so T2 is the only runnable task in the system, and that's why we have this illustrated in this manner. If we work out the performance metrics for this last case, the numbers will look as follows. And again, for all of these, the calculations are posted in the instructor notes. We see that both with respect to throughput and the average wait time, the use of a smaller time slice results in better performance. The only reason why in this case the average completion time is so low that if you look at the calculations, there is a huge variance between the completion time of T1, which is at 11, and then T2, which is way later. We see from this that for I/O-bound tasks, using a smaller time slice is better. The I/O-bound task with a smaller time slice has a chance to run more quickly, to issue an I/O request, or to respond to a user. And with a smaller time slice, we're able to keep both the CPU as well as the I/O devices busy, which makes, obviously, the system operator quite happy. Let's summarize quickly on our question, how long should a time slice be? CPU-bound tasks prefer longer time slices. The longer the time slice, the fewer context switches we'll have to perform, so that basically limits the context switching overheads that the scheduling will introduce. Required to perform useful work, the useful application processing, to as low as possible, and as a result, both the CPU utilization as well as the system throughput as metrics will be as high as possible. On the other hand, I/O-bound tasks prefer shorter time slices. This allows I/O-bound tasks to issue I/O operations as soon as possible, and as a result, we achieve both higher CPU and device utilization, as well as the performance that the user perceives, that the system is responsive and that it responds to its commands and displays output. Let's take a quiz that looks at a problem involving time slices and their values. On a single CPU system, consider the following workload and conditions. We have 10 I/O-bound tasks in the system and 1 CPU-bound task. The I/O-bound tasks issue 1 I/O operation every 1 millisecond of CPU compute time. I/O operations always take 10 milliseconds to complete. The context switching overhead is 0.1 millisecond. And at the end, also, all tasks are long-running, so we're not reporting any kind of execution time for the tasks. Given this, answer first, what is the CPU utilization for a round-robin scheduler with a time slice of 1 millisecond? How about for a 10 millisecond time slice? Provide the two answers here and round them up to the nearest percent value. The formula for computing CPU utilization is provided in the instructor's notes. In the case when the time slice is 1 millisecond, every 1 millisecond, either we will be preempting the CPU-bound task, or the I/O-bound tasks on their own will be stopping because they need to perform an I/O operation every 1 millisecond. So that means that for every 1 millisecond of useful work, we have total of 1 millisecond of the useful work plus 0.1 millisecond of the context switching overhead. So our total useful CPU utilization is 91%. For the case when we have a round-robin scheduler with a 10 millisecond time slice, As we're going through the 10 IO-bound tasks, every single one of them will run just for 1 millisecond, and then we'll have to stop because of issuing an IO request, so we'll have a context switch in that case. So we will perform for the IO-bound tasks 10 times 1 millisecond of useful work, and 10 times 1 millisecond plus 10 times 0.1 millisecond for the context switch. So this is the total amount of total work that has been performed. And then finally, the CPU-bound task will be scheduled, and that one will run for full 10 milliseconds because the time slice value is 10 milliseconds. So that will complete 10 milliseconds of useful work, and then it will complete total of 10 milliseconds plus a context switch time of total time. If we compute this, this comes out to close to 95%. So what this example shows us is that from the CPU's perspective, from the CPU utilization perspective, having a large time slice that favors the CPU-bound task is better. We didn't ask a question of what is the IO utilization for both of these cases. Likely, if we work out the math for that case, we will see that from the perspective of the IO device, it is better to have a smaller time slice. And that will be because the IO device really cannot do anything during this entire period when the CPU-bound task is running for 10 milliseconds with the long time slice. We said earlier that the run queue is only logically a queue. It could also be represented as multiple queues, like when dealing with different priorities, or it could be a tree, or some other type of data structure. Regardless of the data structure, what is important is that it should be easy for the scheduler to find the next thread to run given the scheduling criteria. If we want the IO and CPU-bound tasks in the system to have different time slice values, we have two options. The first option is to maintain a single run queue structure, but to make it easy for the scheduler to figure out easy what type of task is being scheduled so that it can apply the different policy. Another option is to completely separate IO and CPU-bound tasks into two different data structures, two different run queues, and then with each run queue associate a different kind of policy that's suitable for CPU versus for IO-bound tasks. One solution for this is this type of data structure that we'll explain now. It is a multi-queue data structure that internally it has multiple separate queues. Let's say in the first run queue we'll place the most IO-intensive tasks, and we will assign with this run queue a time slice of 8 milliseconds. Let's say for the tasks that are of medium IO intensity, so they have a mix of IO and CPU processing, we have a separate queue in this multi-queue data structure, and here we assign with this queue a time slice of 16 milliseconds. And then for all of our CPU-intensive tasks, we'll use another queue in the multi-queue data structure, and here we'll associate with these a time slice basically that's infinite. So this will be like the first-come, first-served policy. From the scheduler's perspective, the IO-intensive tasks have the highest priority, which means that the scheduler will always check on this queue first, the queue that's associated with the IO-intensive tasks. And the CPU-bound tasks will be treated as tasks with lowest priority, so this queue will be the last one to be checked when trying to figure out what is the next task to be scheduled. So depending on the type of task that we have, we place it in the appropriate queue, and on the other side, the scheduler selects which task to run next based on highest priority, medium, and then lowest. So in this way, we both provide the time slicing benefits for those tasks that benefit for the IO-bound tasks, and avoid the time slicing overheads for the CPU-bound tasks. But how do we know if a task is CPU or IO intensive? How do we know how IO intensive is a task? Now, we can use for that some history-based heuristics, like let this task run and then decide what to do with it, sort of like what we explained with the shortest job first algorithm. But what about new tasks? Or what about tasks that have dynamic changes in their behavior? To deal with those problems, we will treat these three queues not as three separate run queues, but as one single multi-queue data structure. This is how this data structure will be used. When a task first enters the system, so a newly created task, we'll enter it in the topmost queue, the one that has the lowest time slice associated with it. It's like we're expecting that it's the most demanding task when it comes to the scheduling operations, that it will need to be context switched most often. If the task stops executing before these 8 milliseconds, so whether it heals voluntarily or it stops because it needs to wait on an I/O operation, that means we made a good choice. The task is indeed fairly I/O interactive, and so we want to keep the task in this level. So next time around, when it becomes runnable after that I/O operation completes, it will be placed in this exact same queue. However, if the task ends up using up its entire time slice, that means that it was actually more CPU intensive than we originally thought. So we will push it down the next level. It will be preempted from over here, but then the next time it needs to run, it will actually be pushed into this queue. So it will be scheduled from this queue. If the task ends up getting preempted when it was scheduled from this queue, so it used up its entire 60 millisecond time slice, that means that it's even more CPU intensive. So in that case, it will even get pushed down to the bottom queue. So we basically have a mechanism to push the task down these levels based on its historic information. Although we didn't know if a task is I/O or CPU intensive to start with, we made an assumption and then we were able to correct for it. So we assumed that it's I/O intensive and we were able to correct and push it down these levels, down to the lowest most level in case it's CPU intensive. Now, if a task that's in one of the lower queues all of a sudden starts repeatedly releasing the CPU earlier than whatever the time slice specifies because it is waiting on I/O operation, that will be a hint to the scheduler to say, oh, well, this task is more I/O intensive than I originally thought, and it can push it up at one of the queues that are on the higher levels. This resulting data structure is called a multi-level feedback queue. And for the design of this data structure, along with other work on time-sharing system, Fernando Corbata received the Turing Award, which is like the highest award in computer science. It's the equivalent of the Nobel Prize for computing. I want to make sure you don't trivialize the contribution of this data structure and say that it's equivalent to priority queues. First of all, there are different scheduling policies that are associated with each of the different levels that are part of this data structure. More uniquely, however, this data structure incorporates this feedback mechanism that allows us over time to adjust which one of these levels will we place a task in when we're trying to figure out what is the best time-sharing schedule for the mix of tasks in a system. The Linux so-called Of1 Scheduler that we will talk about next uses some of the mechanisms borrowed from this data structure as well. And we won't describe the Solaris scheduling mechanism, but I just want to mention that that's pretty much a multi-level feedback queue with 60 levels, so 60 sub-queues, and also some fancy feedback rules that determine how and when a thread gets pushed up and down these different levels. Let's now look at a couple of concrete examples of schedulers that are part of an actual operating system. First, we will look at the so-called Of1 Scheduler in Linux. The Of1 Scheduler receives its name because it is able to perform task management operations, such as selecting a task from the run queue or adding a task to it, in constant time, regardless of the total number of active tasks in the system. It's a preemptive and a priority-based scheduler, which has a total of 140 priority levels, with 0 being the highest and then 139 the lowest. These priority levels are organized into two different classes. The priority levels from 0 to 99 fall into a class of real-time tasks, and then all others fall into a so-called time-sharing class. All user processes have one of the time-sharing priority levels. Their default priority is 120, but it can be adjusted with a so-called nice value. There's a system call that can be used to do this, and the nice values can be between -20 and 19. So as to span the entire set of time-sharing priorities. The Of1 Scheduler borrows from the multi-level feedback queue scheduler in that it associates different time slice values with different priority levels, and it also uses some kind of feedback from how the tasks behaved in the past to determine how to adjust their priority levels in the future. It differs, however, in how it assigns the time slice values to priorities and how it uses the feedback. It assigns time slice values based on the priority level of the task, similar to what we saw in the multi-level feedback queue scheduling. However, it assigns smallest time slice values to the low priority CPU-bound tasks and it assigns high time slice values to the more interactive, high-priority tasks. The feedback it uses for the time-sharing tasks is based on the time that the task spends sleeping, the time that it was waiting for something or idling. Longer sleep times indicate that the task is interactive. It spent more time waiting, for instance, on user input or on some type of events. Therefore, when longer sleeps are detected, we need to increase the priority of the task, and we do that by actually subtracting 5 in particular from the priority level of the task. In this way, we're essentially boosting the priority, so next time around, this interactive task will execute with higher priority. Smaller sleep times are indicative of the fact that the task is compute-intensive. Therefore, we want to lower its priority, and we do that by incrementing it, by adding the number 5 to it up to a maximum. And essentially, the task next time around will execute in a lower priority class. The run queue in the Of1 Scheduler is organized as 2 arrays of task queues. Each array element points to the first runnable task at the corresponding priority level. These 2 arrays are called active and expired. The active list is the primary one that the scheduler uses to pick the next task to run. It takes constant time to add a task, since you simply need to index into this array based on the priority level of the task, and then follow the pointer to the end of the task list to enqueue the task there. It takes constant time to select a task because the scheduler relies on certain instructions that return the position of the first set bit in a sequence of bits. So if the sequence of bits corresponds to the priority levels, and a bit value of 1 indicates that there are tasks at that priority level, then it will take a constant amount of time to run those instructions to detect what is the first priority level that has certain tasks on it. And then once that position is known, it also takes a constant time to index into this array and select the first task from the run queue that's associated with that level. If tasks yield the CPU to wait on an event or are preempted due to higher priority task becoming runnable, the time they spend on the CPU is subtracted from the total amount of time, and if it is less than the time slice, they are still placed on the corresponding queue in the active list. Only after a task consumes its entire time slice will it be removed from the active list and placed on the appropriate queue in the expired array. The expired array, that contains the tasks that are not currently active in the sense that the scheduler will not select tasks from the expired array as long as there are still tasks on any of the queues in the active array. When there are no more tasks left in the active array, at that point the pointers of these 2 lists will be swapped, and the expired array will become the new active one, and vice versa, the active array will start holding all of the tasks that are removed from the active array and are becoming inactive. This also explains the rationale why in the Of1 Scheduler, the low priority tasks are given low time slices and the high priority tasks are given high time slices. As long as the high priority tasks have any time left in their time slice, they will keep getting scheduled. They will remain in one of the queues in the active array. Once they get placed on the expired array, they will not be scheduled, and therefore we want the low priority tasks to have a low time slice value so that, yes, they will get a chance to run, however, they won't disrupt the higher priority tasks, they won't delay them by too much. Also note that the fact that we have these 2 arrays also serves like an aging mechanism, so these high priority tasks will ultimately consume their time slice, be placed on the expired array, and ultimately the low priority tasks will get a chance to run for their small time amount. The Of1 Scheduler was introduced in the Linux kernel 2.5 by Ingo Molnar. In spite of its really nice property of being able to operate in constant time, the Of1 Scheduler really affected the performance of interactive tasks significantly. And as the workloads changed, as typical applications in the Linux environment were becoming more time-sensitive, think Skype, movie streaming, gaming, the jitter that was introduced by the Of1 Scheduler was becoming unacceptable. For that reason, the Of1 Scheduler was replaced with the Completely Fair Scheduler, and the CFS Scheduler became the default scheduler starting in the Linux 2.6.23 kernel. Ironically, both of these schedulers are developed by the same person. You should note that both the Of1 and the CFS Scheduler are part of the standard Linux distribution. This one is the default. However, if you wish, you can switch and choose the Linux Of1 Scheduler to execute your tasks. As we said, one problem with the Of1 Scheduler in Linux is that once tasks are placed on the expired list, they won't be scheduled until all remaining tasks from the active list have a chance to execute for whatever their time slice amount of time is. As a result, the performance of interactive tasks is affected. There is a lot of jitter. In addition, the scheduler in general doesn't make any fairness guarantees. There are multiple formal definitions of fairness, but intuitively you can think of it that in a given time interval, all of the tasks should be able to run for an amount of time that is proportional to their priority. And for the Of1 Scheduler, it's really hard to make any claims that it makes some kind of fairness guarantees. As we said, Ingo Molnar proposed the Completely Fair Scheduler, CFS, to address the problems with the Of1 Scheduler, and CFS is the default scheduler in Linux since the 2.6.23 kernel. It's the default scheduler for all of the non-real-time tasks. The real-time tasks are scheduled by a real-time scheduler. The main idea behind the Completely Fair Scheduler is that it uses a so-called red-black tree as a run queue structure. Red-black trees belong to this family of dynamic tree structures that have a property that as nodes are added or removed from the tree will self-balance itself so that all the paths from the root to the leaves of the tree are approximately of the same size. You can look at the instructor notes for a link for more information about this type of data structure. Tasks are ordered in the tree based on the amount of time that they spend running on the CPU, and that's called virtual runtime. CFS tracks this virtual runtime in a nanosecond granularity. As we can see in this figure, each of the internal nodes in the tree corresponds to a task, and the nodes to the left of the task correspond to those tasks which had less time on the CPU. They had spent less virtual time, and therefore they need to be scheduled sooner. The children to the right of a node are those that have consumed more virtual time, more CPU time, and therefore they don't have to be scheduled as quickly as the other ones. The leaves in the tree really don't play any role in the scheduler. The CFS scheduling algorithm can be summarized as follows. CFS always schedules the task which has the least amount of time on the CPU, so that typically would be the leftmost node in the tree. Periodically, CFS will increment the vRuntime of the task that's currently executing on the CPU, and at that point, it will compare the virtual runtime of the currently running task to the vRuntime of the leftmost task in the tree. If the currently running task has a smaller vRuntime compared to the one that's in the leftmost node in the tree, the currently running task will continue executing. Otherwise, it will be preempted and it will be placed in the appropriate location in the tree. Obviously, the task that's corresponding to the leftmost node in the tree will be the one that will be selected to run next. To account for differences in the task priorities or in their niceness value, CFS changes the effective rate at which the task's virtual time progresses. For lower priority tasks, time passes more quickly. Their virtual runtime value progresses faster, and therefore they will likely lose their CPU more quickly because their virtual runtime will increase compared to other tasks in the system. On the contrary, for high priority tasks, time passes more slowly, their virtual runtime value will progress at a much slower rate, and therefore they will get to execute on the CPU longer. You should take note of the fact that CFS uses really one run queue structure for all of the priority levels, unlike what we saw with some of the other scheduler examples. In summary, selecting a task from this run queue to execute takes Of1 time, takes constant amount of time since it's typically just a matter of selecting the leftmost node in the tree. At the same time, adding a task to the run queue takes logarithmic time relative to the total number of tasks in the system. Given the typical levels of load in current system, this log of n time is acceptable. However, as the compute capacity of the nodes continues to increase and systems are able to support more and more tasks, it is possible that at some point the CFS scheduler will be replaced by something else that will be able to perform better when it comes to this second performance criteria. As a review, I would like to ask a question about the two Linux schedulers that we just discussed. What was the main reason the Linux Of1 Scheduler was replaced by the CFS scheduler? Was it because scheduling a task under high load took unpredictable amount of time? Low priority tasks could wait indefinitely and starve? Or because interactive tasks could wait unpredictable amounts of time to be scheduled to run? Select the appropriate answer. Let's take a look at each of the choices that are given. The first statement is not correct. The Linux Of1 scheduler was Of1 because it took constant amount of time to select and schedule a task regardless of the load. The second statement is sort of correct in the sense that as long as there were continuously arriving higher priority tasks, it was possible for the low priority task to keep waiting an unpredictable amount of time and possibly indefinitely and therefore starve. But this was really not the main reason why the scheduler was replaced. The final choice was the main reason. Recall that we said that the common workloads were becoming much more and more interactive and were demanding high predictability. In the Of1 scheduler with the active and expired lists, once a task was moved to the expired list, it had to wait there until all of the low priority tasks consumed their entire time quantum. For a very long time, Linus Torvalds resisted integrating a scheduler that would address the needs of these more interactive tasks in the Linux kernel. His rationale was that Linux was supposed to be a general-purpose operating system and should not necessarily be addressing any of the needs of some more real-time or more interactive tasks, and therefore he liked the simplicity of the Of1 scheduler. However, as the general-purpose workloads began to change, then a general-purpose operating system like Linux had to really incorporate a scheduler that would address the needs of those general-purpose workloads, and CFS was really meeting those needs. Let's now look at scheduling on multi-CPU systems. However, before we start talking about scheduling, let's look a little bit at some architecture detail. First, we will look at shared memory multiprocessors. And then we will also take a look at how this compares to multi-core architectures. In a shared memory multiprocessors, or SMPs, there are multiple CPUs. Each of them have their maybe own private caches like L1 and L2. There are last level caches that may or may not be shared among the CPUs. And there is a system memory, DRAM, that is shared across all of the CPUs. Here we show just one memory component, but it is possible that there would be multiple memory components, but the point is that all of the memory in the system is shared among all of the CPUs. In the current multi-core world, each of these CPUs can have multiple internal cores, so multiple CPUs internally. Each of those cores will have private caches, and then overall, the entire multi-core CPU will have some shared last-level cache, and then again, there will be some shared system memory. Here in this picture, we have a CPU with 2 cores, so that's a dual-core processor, and this is more common for client devices like laptops, for instance, or even cell phones today can have 2 CPUs. Whereas on the server and platforms, it's more common to have CPUs that have 6 or 8 cores, and to also have multiple such CPUs, so we'll have multiple multi-core CPUs. As far as the operating system is concerned, it sees all of these CPUs, as well as the cores in a CPU, as entities onto which it can schedule execution context, so threads. So all of these are, as far as the operating system is concerned, possible CPUs where it can schedule some of its workload. So to make our discussion more concrete, we will first start talking about scheduling on multi-CPU systems in the context of SMP systems, and a lot of these things will apply to the multi-core world, because again, the scheduler just sees the cores as CPUs. And we'll make some comments that are more exclusively applied to multi-cores towards the end of this lesson. We said in our earlier lectures that the performance of threads and processes is highly dependent on whether the state that the thread needs is in the cache or in memory. Let's say a thread was executing on CPU 1 first. Over time, this thread was likely able to bring a lot of the state that it needs both into the last level cache that's associated with the CPU as well as in the private caches that are available on the CPU. And in this case, when the caches are hot, this helps with the performance. Now, the next time around, if the thread is scheduled to execute on the other CPU, none of its state will be there, so the thread will operate with a cold cache. We'll have to bring all of the state back in, and that will affect performance. Therefore, what we want to achieve with a scheduling on multi-CPU systems is to try to schedule the thread back on the same CPU where it executed before because it is more likely that its cache will be hot. We call this cache affinity, and that is clearly important. To achieve this, we basically want the scheduler to keep a task on the same CPU as much as possible. To achieve this, we can maintain a hierarchical scheduler architecture where at the top level, a load balancing component divides the tasks among CPUs, and then a per-CPU scheduler with a per-CPU run queue repeatedly schedules those tasks on a given CPU as much as possible. To balance the load across the different CPUs and their per-CPU run queue, the top-level entity in the scheduler can look at information such as the length of each of these queues to decide how to balance tasks across them. Or potentially when a CPU is idle, it can at that point start looking at the other CPUs and try to get some more work from them. In addition to having multiple processors, it is possible to also have multiple memory nodes. The CPUs and the memory nodes will be interconnected via some type of interconnect. For instance, on modern Intel platforms, there is an interconnect that's called Quick Path Interconnect, or QPI. One way in which these memory nodes can be configured is that a memory node can be technically connected to some subset of the CPU, so for instance to a socket that has multiple processors. If that is the case, then the access from that set of CPUs to the memory node will be faster versus from that particular processor to a memory node that's associated with another set of CPUs. Both types of accesses will be made possible because of the interconnect that's connecting all of these components. However, they will take different amount of time. We call these types of platforms non-uniform memory access platforms, or NUMA platforms. So then clearly, from a scheduling perspective, what would make sense is for the scheduler to divide tasks in such a way that tasks are bound to those CPUs that are closer to the memory node where the state of those tasks is. We call this type of scheduling NUMA-aware scheduling. The reason why we have to context switch among threads is because the CPU has one set of registers to describe the active execution context, the thread that's currently running on the CPU. These include the stack pointer and program counter in particular. Over time, however, hardware architects have recognized that they can do certain things to help hide some of the overheads associated with context switching. One way this has been achieved is to have CPUs that have multiple sets of registers, that each set of register can describe the context of a separate thread, of a separate execution entity. One term that's used to refer to this is hyperthreading. So hyperthreading refers to multiple hardware-supported execution contexts, hyperthreads. There's still just one CPU, so on the CPU, only one of these threads can execute at a particular moment of time. However, the context switching between these threads is very fast. And just basically, the CPU needs to switch from using this set of registers to another set of registers. Nothing has to be saved or restored. This mechanism is really referred to by multiple names. So in addition to hyperthreading, a common term is also to refer to this as hardware multithreading, or chip multithreading, or simultaneous multithreading, SMTs. So we will use basically these two terms, hyperthreading and SMTs, more dominantly than the others. Hardware today frequently supports 2 hardware threads. However, there are multiple higher-end server designs that support up to 8 hardware threads. And one of the features of today's hardware is that you can enable or disable this hardware multithreading at boot time, given that there are some trade-offs associated with this, as always. If it is enabled, as far as the operating system is concerned, each of these hardware contexts appears to the operating system scheduler as a separate context, a separate virtual CPU onto which it can schedule threads, given that it can load the registers with the thread context concurrently. So for instance, in this figure, the scheduler will think that it has two CPUs and it will load these registers with the context of these two threads. So one of the decisions that the scheduler will need to make is which two threads to schedule at the same time to run on these hardware contexts. To answer that question, let's remind ourselves of what we talked about when we talked about the context switching time. We said that if the time that a thread is idling, that a thread has to wait on something to happen, is greater than twice the time to perform a context switch, then it makes sense to actually do the context switch in order to hide this waiting, this idling latency. In SMT systems, the time to perform a context switch among the two hardware threads is on the order of cycles. And the time to perform a memory access operation, a memory load, remains on the order of hundreds of cycles, so it's much greater. So given this, then it means that it does make sense to context switch to the other hardware thread, and in that way, this technology, hyperthreading, will help us even hide the memory access latency that threads are experiencing. Hyperthreading does have implication on scheduling in that it raises some other requirements when we're trying to decide what kinds of threads should we co-schedule on the hardware threads on a CPU. We will discuss this question in the context of the paper Chip Multithreaded Processors Need a New Operating System Scheduler by Sasha Fedorova and others. To understand what's required from a scheduler in a simultaneous multithreading system, let's make some assumptions first. Since we will base our discussion on Fedorova's paper, we will use the same assumptions that she has made, and the figures that we will use to illustrate those assumptions will be reproductions from her paper and her presentation. The first assumption that we will make is that a thread can issue an instruction on every single cycle. So that means that a CPU-bound thread, a thread that just issues instructions that need to run on the CPU, will be able to achieve a maximum metric in terms of instructions per cycle, and that will be instructions per cycle equal 1. Given that we have just one CPU, we cannot have an IPC that is greater than 1. The second assumption that we will make is that a memory access takes 4 cycles. What this means is that a memory-bound thread will experience some idle cycles while it's waiting for the memory access to return. We will also assume that the time it takes to context switch among the different hardware threads is instantaneous, so we won't take any overheads over that into consideration. And also, to start with, for the sake of our discussion, let's assume that we have a SMT with 2 hardware threads. Let's take a look first at what would happen if we chose to co-schedule on the 2 hardware contexts 2 threads that are both compute-bound, so compute-intensive or CPU-bound. What that means is that both of the threads are ready to issue a CPU instruction on every single cycle. However, given that there is only one CPU pipeline, so one CPU fetch, decode, issue, ALU logic, only one of them can execute at any given point of time. As a result, these 2 threads will interfere with each other. They will be contending for the CPU pipeline resources, and best case, every one of them will basically spend 1 cycle idling while the other thread issues its instruction. As a result, for each of the threads, its performance will degrade by a factor of 2. Furthermore, looking at the entire platform, we will notice that in this particular case, our memory component, the memory controller, they're idle. There's nothing that's scheduled that performs any kinds of memory accesses. Well, that's not good either. Well, another option is to co-schedule 2 memory-bound threads. In this case, we see, however, that we end up with some idle cycles because both of the threads end up issuing a memory operation, and then they need to wait 4 cycles until it returns. Therefore, we have 2 of the cycles that are unused. So the strategy then to co-schedule memory-bound threads leads to wasted CPU cycles. So then our final option is to consider mixing some CPU and memory-intensive threads. And then if we see, we end up with the desired schedule. It's bingo. We end up fully utilizing each processor cycle. And then whenever there is a thread that needs to perform a memory reference, we context switch to that thread in hardware. The thread issues the memory reference, and then we context switch back to the CPU-intensive thread until the memory reference completes. Scheduling a mix of CPU and memory-intensive threads allows us to avoid or at least limit the contention on the processor pipeline, and then also all of the components, both the CPU and the memory, will be well utilized. Note that this still will lead to some level of degradation due to the interference between these two threads. For instance, the compute-bound thread can only execute 3 out of every 4 cycles compared to when it ran alone. However, this level of degradation will be minimal given the properties of the particular system. While the previous example gave us a good idea what type of scheduler to use, that the scheduler should mix CPU and memory-bound tasks, the question that is open at this point is how do we know if a thread is CPU-bound versus a memory-bound? To answer this question, we will use historic information. We will look at the thread's past behavior, and this is similar to what we said was useful when we were trying to determine whether a thread is interactive or I/O-bound versus CPU-bound. However, previously we used sleep time for this type of differentiation of I/O versus CPU-bound, and that won't work in this case. First of all, the thread is not really sleeping when it's waiting on a memory reference. The thread is active and it's just waiting in some stage in the processor pipeline and not on some type of software queue. Second, to keep track of the sleep time, we were using some software methods, and that's not acceptable. We cannot execute in software some computations to decide whether a thread is CPU-bound or memory-bound, given the fact that the context switch takes order of cycles, so the decision what to execute should be very, very fast. Therefore, we somehow need some kind of hardware support, some information from the hardware in order to be able to answer this question. Fortunately, modern hardware has lots of so-called hardware counters that get updated as the processor is executing and keep information about various aspects of the execution. These include information about the cache usage, for instance, such as the L1, L2, or the last level cache misses, or information about the number of instructions that were retired so that we can compute the IPC. Or on newer platforms, there is also information regarding the power or energy usage of the CPU or particular components of the system. There are a number of interfaces and tools that can be used to access these hardware counters via software. For instance, OProfile or the Linux Perf tool are available in Linux, and one of the things that's useful is that if you look at the OProfile website, it actually has a list of all of the hardware counters that are available for different architectures, because the hardware counters are not uniform on every single platform. So then how can hardware counters help a scheduler make any kinds of scheduling decisions? Many practical as well as research-based scheduling techniques rely on the use of hardware counters to understand something about the requirements of the threads in terms of the kinds of resources that they need, CPUs or memory. So then the scheduler can use that information to pick a good mix of the threads that are available in the run queue to schedule on the system so that all of the components of the system are well utilized, or so that the threads don't interfere with one another, or whatever other scheduling policy needs to be achieved. For instance, a scheduler can look at a counter like the last level cache misses. And using this counter, a scheduler can decide that a thread is memory bound, so its footprint doesn't fit in the cache. Or the same counter can also tell the scheduler that something changed in the execution of the thread, so that now it's executing with some different data in a different phase of its execution, and it's running with a cold cache. What this tells us is that one counter can tell us different things about a thread. So given that there isn't a unique way to interpret the information provided from hardware counters, we really sort of guesstimate what it is that they're telling us about the thread's resource use. That doesn't mean that the use of hardware counters is not good. In fact, schedulers can use hardware counters to make informed decisions regarding the workload mix that they need to select. They would typically use some combination of the counters that are available on the CPU, not just one, in order to build a more accurate picture of the thread's resource needs. And they would also rely on some models that have been built for a specific hardware platform and that have been trained using some well-understood workloads. So, we ran a workload that we know is memory intensive, and we made some observations regarding the values of those counters, and therefore we now know how to interpret them for other types of workloads. These types of techniques really fall into much more advanced research problems, which are a little bit out of the scope of this particular introductory course. However, I really wanted to make sure that you are aware of the existence of these hardware counters and how they can be used and how they can be really useful when it comes to resource management in general, not just regarding CPU scheduling. As a more concrete example, Fedorova speculates that a useful counter to use to detect the thread's CPU-ness versus memory-ness is cycles per instruction. She observes that a memory-bound thread takes a lot of cycles to complete an instruction, therefore it has a high CPI, whereas a CPU-bound thread, it will complete an instruction every cycle or near that, and therefore it will have a CPI of 1 or a low CPI. So then she speculates then it would be useful to gather this kind of information, this counter about the cycles per instruction, and use that as a metric in scheduling threads on hyper-threaded platforms. Given that there isn't exactly a CPI counter on the processors that Fedorova uses in her work, and computing something like 1 over IPC would require software computation, so that wouldn't be acceptable. For that reason, Fedorova uses a simulator that supposedly the CPU does have a CPI counter, and then she looks at whether a scheduler can take that information and make good decisions. Her hope is that if she can demonstrate that CPI is a useful metric, then hardware engineers will add this particular type of counter in future architectures. To explore this question, she simulates a system that has 4 cores where every one of the cores is 4-way multi-threaded. So there is a total of 16 hardware contexts in her experimental testbed. Now she wants to vary the threads that get assigned to these hardware contexts based on their CPI. So she creates a synthetic workload where her threads have a CPI of 1, 6, 11, and 16. Clearly, the threads with a CPI of 1 will be the most CPU intensive, and then the threads with a CPI of 16 will be the most memory-intensive threads. And the overall workload mix has 4 threads of each kind. And then what she wants to evaluate is what is the overall performance when a specific mix of threads gets assigned to each of these 16 hardware contexts. To understand the performance impact of such potentially different scheduling decisions, she uses as a metric the instructions per cycle. Given that the system has 4 cores in total, the maximum IPC that could be achieved is going to be 4. So 4 instructions per cycle will be the best case scenario where every single one of the cores completes 1 instruction in each cycle. And then she conducts several experiments as shown in this figure. In every one of the experiments, she manually and statically changes how the workload is distributed across the cores. So in the first experiment on core 1, the 4 hardware threads will be assigned software threads that have a CPI of 1, 6, 11, and 16. The 4 hardware threads on core 2 will be assigned software threads or tasks that have CPI of 1, 6, 11, and 16, and so forth. In the first experiment, every one of the cores runs identical mix, where each hardware thread runs a task with a different CPI. And then in the last experiment, each of the cores runs a very different kinds of mix, where on core 0, all of the tasks are CPU intensive. They have a CPI of 1, whereas on core 3, all of the tasks are memory intensive because they have a CPI of 16. And then the second and the third round of the experiments fall somewhere between these 2 extremes. So what she's trying to do, she's trying to make some static decisions that a scheduler would have made. And in doing that, she's trying to understand whether it even makes sense to build a scheduler that will use CPI as a metric. Instead of a typical quiz, I would like for you to do a self-check of your analytical skills. Here is a diagram that's summarizing the performance results that Fedorova gathered from running the experiments that we showed before. What do you think these results tell us about the use of a metric like cycles per instruction for scheduling? Again, this is not really a quiz, this is more a self-check of your analytical skills. Try answering this question and then see our summary of the results of using CPI as a scheduling metric in the next video. Here are the conclusions that we can draw from these results. If we look at the cases for A and B, if we remember from the table that we saw with the actual experiments, in these cases, we had a fairly nice mix of tasks with different CPI values on each of the cores. So in these cases, the processor pipeline was well utilized and we're obtaining a high IPC. It is not the maximum IPC of 4, so the maximum performance that one can obtain on the processor that Fedorova is simulating, but it's fairly high. If we look at the cases for C and D, in these experiments, each of the cores was assigned tasks that had much more similar CPI values. In fact, in the case of D, every single one of the cores ran tasks that had the exact same CPI value. So if we take a look at these results, we see that the total IPC is much lower than what we saw for the case A and B. The reason for that is that on some cores, like on core 0 in particular, but also on core 1, there is a lot of contention for the CPU pipeline. So these are the cores that mostly had tasks with a low CPI. So mostly the compute-intensive tasks were here. On the other hand, cores 2 and 3, they contribute very little to the aggregate IPC metric. So basically, they really execute only very few instructions per cycle, or a small percentage of an instruction per cycle, rather, given that a maximum is 1. The reason for that is that we mostly have memory-intensive tasks on these two cores, and that leads to wasted cycles on them. So by running this experiment, Fedorova confirmed her hypothesis that running tasks that have mixed CPI value is a good thing, that will lead to an overall high performance of the system. So the conclusion from these results is that CPI is a great metric, and therefore we should go ahead and build hardware that has a CPI hardware counter and tracks this value, so that we can then go ahead and also build operating system schedulers that use this value in order to schedule the right workload mix. Not so fast. In our discussion so far, in the experimental analysis, we used workloads that had CPI values of 1, 6, 11, and 16. And the results showed that if we have such a hypothetical workload that has such distinct and widely spread out CPI values, the scheduler can be effective. But the question is, do realistic workloads have CPI values that exhibit anything that we used in the synthetic workload? To answer this, Fedorova profiled a number of applications from several benchmark suites. And these benchmark suites are widely recognized in industry and in academia as well, that they include workloads that are representative of real-world relevant applications. And let's look at the CPI values for all of these benchmarks. We see that they're all sort of cluttered together. There aren't such distinct CPI values like 1, 6, 11, and 16 as what she used in her experimental analysis. What this tells us is that, although in theory it seems like a great idea to use cycles per instruction as a scheduling metric for hyper-threaded platforms, in practice, real workloads don't have behavior that exhibits significant differences in their CPI value, and therefore CPI really won't be a useful metric. So I showed you a paper about something that doesn't work. There's still some very important takeaways from this paper. First, you learned about SMTs and some of the resource contention issues there, specifically regarding the processor pipeline as a resource. Next, you learned how to think about the use of hardware counters to establish some kind of characteristics about the workload, to understand it better so that you can better inform the operating system level resource management. In addition, you learned that it is important to design schedulers that will also think about resource contention, not just about load balancing. For instance, a scheduler should think about choosing a set of tasks that are not going to cause a resource contention with respect to the processor pipeline or the hardware cache or the memory controller or some type of I/O device. So these principles generalize to other types of resources, not just to the processor pipeline in hardware multi-threaded platforms. And by the way, in Fedorov's follow-on work, as well as several other efforts, it's been established that a particularly important contributor to performance degradation when you're running multiple tasks on a single hardware multi-threaded or multi-core platform is the use of the cache resource, in particular the last level cache. So what that has told us is to, for instance, keep track of how a set of threads is using the cache as a resource and pick a mix that doesn't cause contention on the last level cache usage. And this is just for your information. We're not going to look in any additional papers that really further explore this issue, not in this course at least. In summary, you should now know how scheduling works in an operating system. We discussed several scheduling algorithms and the corresponding run queue data structures that they use. We described two of the schedulers that are default in the Linux kernel, the Completely Fair Scheduler and its predecessor, the Linux Of1 Scheduler. And also we discussed some of the issues that come up in scheduling when considering multiple CPU platforms. This, we said, includes platforms with multiple CPUs that share memory, multi-core platforms, as well as platforms with hardware-level multi-threading. As a final quiz, please tell us what you learned in this lesson. Also, we would love to hear your feedback on how we might improve this lesson in the future.